The last portion of section 8.3 is developing the sum of a finite and an infinite geometric sequence. So the formula we're going to use in order to solve this is when my ratio is not 1, I need to either be increasing or decreasing, I'm going to say a sub 1 times 1 minus r to the n all over 1 minus r. That is going to give me the summation of everything in my geometric series. So with this, I need to find a sub 1, so I need my first term, I need the common ratio, and I need the number of terms. So those are the three things that I need in this formula. I need a sub 1, I need r, and I need n. So in my first example there, I see that I have n equaling 1 through 20, 2 times 0.1 raised to the n. So for this, I want to start plugging in values. I need to find a sub 1. And the way I get a sub 1 is I plug 1 into my original. So this formula, if I were to work it out the old way, would be 2 times 0.1 raised to the first plus 2 times 0.2 squared plus 2 times 0.2 cubed all the way up to 2 times 0.2 raised to the 20th. This first piece right here is a sub 1. The second part is a sub 2. The third part is a sub 3. All the way through a sub 20. So with that, I need to now plug those values into my formula. My common ratio I already have. It's the piece that is inside the parentheses, which in this case is the 0.1. So right here is my r value. So let's plug in what I know. I want to find the summation of the first 20 terms. I know a sub 1 is 2 times 0.1 raised to the first, which is going to be 0.2. And I need 1 minus my common ratio. The common ratio is 0.1 raised to the 20th. All over 1 minus 0.1. And we'll plug all that into our calculator. And when you plug all that into your calculator, you get that this is equal to 0.2. And there's a bunch of 2's there. So it looks like it's 0.2 repeating. The second example, we want to find the summation from n equaling 1 up to 15. So we want to find the first 15 terms of this geometric sequence. Once again, we need a1, we need r, and we need n. Well, n is 15. The common ratio is what's in parentheses, negative 1/3. We need to find a sub 1. And a sub 1 is found out by plugging 1 in for n. So 2 times negative 1/3 raised to the first, which is negative 2/3. So a sub 1 is equal to negative 2/3. So a plug in, s sub 15 is equal to negative 2/3 times 1 minus a negative 1/3 raised to the 15th all over 1 minus a negative 1/3, and you get this long 0.500000348, which is the summation of that formula. Now, a lot of people would fall into the trap of saying right here, this 2 here would be a sub 1. Because in the formula you looked at before, you said a sub 1 times r raised to the n minus 1 for a geometric sequence. You might think, okay, a sub 1 here is going to be 2, so I'll just plug in 2 there. Or here, there would be 2, because the first number there should be a sub 1. But remember, a sub 1 is the result of plugging in your first term, or plugging in 1. The only time that this ends up being a sub 1 is if this here is going to be n minus 1. Because then if I have n equaling 1, I have an n minus 1 up there. 1 minus 1 is 0. anything raised to the 0 power is 1, so this whole quantity would be 1, and then 2 times 1 would be 2. So that a sub 1 piece in front here as being a sub 1 is only the case if your expression here is raised to the n minus 1, or if I were to say n equals 0 and start off with 0 right there, because then anything raised to that 0 is going to be 1, and then 1 times that quantity is going to be the same, which would be a sub 1. The second concept along with summations is when we have an infinite geometric sequence or series. And there's two cases. One case is when the absolute value of r is less than 1, we say the series converges. And I am going to come up with an actual answer even though I'm adding an infinite number of terms. Something where r is going to be greater than 1 or r is less than negative 1, then I'm going to go off to infinity, and that's what we call diverging. It diverges. I can't get a sum because everything keeps getting larger. So with this, we want to use the formula a sub 1 over 1 minus r in order to come up with my infinite summation. And this is actually a lot more simple than the one we had up here at the top. And you can see the work on how we get that right there. You might also see the situation here where n equals 0 up to infinity. And if that's the case, we've got a sub 1 raised to the rn is equal to a sub 1 over 1 minus r. So realize here you could have n equaling 1 or n equaling 0 when you solve these out. So the last two examples are dealing with an infinite series. And in order to do an infinite series, I need to use the formula a sub 1 over 1 minus r, because we have the infinite. So I need to find a sub 1, I need to find r. Now r is easy because it's the piece that is inside the parentheses. So there's r. And here, a sub 1, we find a sub 1 by plugging 1 into my equation. So 2 times 0.4 raised to the n minus 1. So here's a situation where that front value is a sub 1. That value is a sub 1 because if I plug in a 1 to the n minus 1, that quantity goes to 0, and then anything raised to the 0 is 1, so that 2 is my a sub 1. So here, a sub 1 is 2, 1 minus r, which is 0.4, that equals 10/3. So I actually get a regular number for something that I add infinitely. The second example, n equals 1 to infinity of negative 10 times 0.02 raised to the n. This one we don't have that n minus 1 up there, so I can't just say my a sub 1 is going to be 10. So I need to find my a sub 1. A sub 1 is the result of plugging in 1 for n. So negative 10 times 0.2. So a sub 1 is going to be negative 2. My r right there is the value that is inside the parentheses. So a sub 1 over 1 minus r. A sub 1 is negative 2. And then 1 minus r, which is 0.2. So negative 2 over 1 minus 0.2 is a negative 5/2. So once again, even though we have an infinite series up there, we end up with a whole number as our answer.